Today we will look at some of the methods to find the solutions of nonlinear equations. So that will be the topic of discussion today. So solutions of nonlinear equations. Nonlinear equations. Okay, that's what we would want to discuss today. So we saw in the last lecture that we have to find solutions of polynomials of the form. So we wrote some polynomial of the form an. So we had a0 plus a1x plus a2x squared of this form. So then we have to find the roots, or what we call the roots of this polynomial equation. We saw this in the case of a characteristic polynomial to determine the eigenvalues of a matrix. So this is one example where we have to find the solution of a nonlinear equation. Finally, the roots of this polynomial is nothing but saying that this is equal to 0 and finding the solutions of those equations. So we will discuss some of these methods. So we saw one method of doing that, that is dividing this by a quadratic polynomial and finding the factorizing this polynomial into a polynomial of this order, that we will write Pn of x as some p primed n minus 2 of x into some other polynomial which you would call in this case as y2 of x. So we had a quadratic equation, quadratic polynomial multiplying this n minus 2th order polynomial, and then we knew we could find the roots of this. So now this is equal to 0, as definitely has one root as y2 of x equal to 0, y2 being a quadratic polynomial, and we know how to find closed form solutions of quadratic polynomial. Right. So in general, finding the solutions of the nonlinear equation will not be so trivial. And it occurs in many times that we have complicated nonlinear equations and which are not of just simple quadratic form. Right. So one example is, of course, is to get the nonlinear equation into factorize the nonlinear equation, nonlinear function which you have into a quadratic function multiplied by another function, and then we can find the one of the roots as the roots of this quadratic equation. That's what we did in this case of a polynomial equation. But not all nonlinear equations will be in polynomial form, so we may not be able to do this factorization quite easily. In this case, it was easy to do this factorization and write it as a quadratic function and then finding a solution of that. But this may not be always easy. And it will not be always easy to find, in the general case of a nonlinear equation, it may not be easy to find a closed form solution of this form at all. So here in the case of quadratic equation, we know that we have closed form solutions of this form, but if this is more complicated functions, it is not even obvious that we have closed form solutions. So the question is, what do we do? Then we obviously will go into some numerical technique of finding the solutions of that. So in the case where closed form solutions are difficult, okay, we would or impossible to find. Okay, so we would solve the nonlinear equations of this form f of x equal to 0 using some numerical technique. So one of the ways, the first thing one should do when you get an equation of this form, that is any nonlinear function of f of x, and you have to find the roots of this equation. That is, if you are just given an equation of the form f of x equal to 0 and you are asked to find the roots of this equation, what we do is just to plot this function f of x. If it's a simple function to plot, okay, then we would just plot it. Okay, so then we would have, if it's especially if it's a case like this, and we would plot f of x versus x. We just plot this function. Okay, so that, and then let's say this function. So that's our y equal to 0. So that's a y equal to 0 or f of x equal to 0 line. Okay. And then if you have a function which behaves something like this, Okay, now all these crossing points are solutions of this equation. Or in another sense, the solution of this equation is just the same as the zeros of this function, right? So we just have to find where this function crosses the axis, the x-axis, or the f of x equal to 0 line. Okay, so that will be the simplest method. Okay, so if you are at least to get an idea of, maybe may not be very accurate if by visual thing, but at least that's the simplest method, and it is the first. It may be a good method to find get at least an approximate value of the zeros of this function f of x. So these are the points at with this, let me call them x1, x2, x3, x4. So we have x1, x2, x3, x4. Okay, so now these are the 4 points for which this function goes to 0. So that's the solutions of these equations. Okay, so at least we found 4 such roots. Okay, so that's a simple graphical method to do that. So note another important property, that whenever this function, whenever near the 0, right, near one of the zeros, near x1, x2, x3, and x4, this function would change sign, right? So that is a 0. So obviously this is negative here and positive on this side. So when the function goes past its solution, right, one of the roots, okay, and then it would change its sign. Okay, so we can use that in other methods. That is, we could use in many of the iterative schemes, we would use this property that the function changes sign when it goes through the root, unless in a very special case where it just touches there and then goes away. We will not discuss such cases. Okay. So here is cases in which this function crosses the axis, that f equal to 0 line. Okay, so with it changes sign, so we can use that property and in iterative schemes. So that's something which you would be using. Okay. So in general way is to first do this, plot this function, and then look at the solutions by inspection. Right. So that is called the graphical method, or do make a guess for the solution. So even by plotting, we could only get a guess for the solutions because the accurate values may be difficult to read off from a graph. Okay, but then we know that the function changes sign at this point. Okay, so we could iterate around that point and then get to the value to decide accuracy. Okay. So in general, we have 4 different methods of doing this. Okay, so the first one which I discussed is a graphical method, and all others, that is the method of successive bisection, which we will discuss in detail, Newton-Raphson's iterative method, or secant methods. All these methods are basically iterative methods, that you make a guess solution and you iterate around that. So all these 3 methods. So I would classify this as 2 basic methods. One is the graphical methods, okay, another is iterative methods. We will see. So the graphical method is what I just described here on the board, that is just just plotting the function and then looking at where it actually crosses the 0 axis. And now we will look at so the method of successive bisection. So that's what we do. We just use this property that the function changes sign at this value. So we will make a guess value. We guess. So it's not enough to make one guess. We have to make 2 guesses. Okay. So we'll do that. I'll just replot this function again. So let's say that's my x is equal to 0 line. Okay, and my function is something like this. Okay, so then I will make I have to make 2 guesses. Okay, so one x1 and x2. Okay, so we choose x1 to be such that it is positive. So that I call this as x1 and this as x2. Okay, that's my x-axis. So that's the idea. So we have to make 2 points. Okay, in this case x0 and x1. Sorry. So x0 and x1. We choose x0 and x1. Okay, so such that f of x0 and f of x1 are opposite signs. Okay, so we chosen f of x0 to have to be negative and f of x1 to be positive. Just choice. So the basic idea in the method of successive bisection is to choose, first make a guess, okay, such that of 2 points, okay, such that it is on either side of a root. Okay, now there can be dangers in this. Okay, we'll discuss that. For example, the initial guess has to be reasonably good, that if the function has multiple roots, and if you choose if the function has multiple roots, now let's say it goes like this. And if you choose one to be here and one to be here, okay, so that is if you choose your initial guess to be somewhere here, again one here, okay, and then again this function has changed sign. Of course, this is positive here, this is negative here, but then we will not iterate it to into the correct root. So it has to be reasonably close, the solutions, okay, and we have to have an idea that there are no multiple roots, we don't have multiple roots within this interval. Okay. So that's one of the problems with this successive bisection. That is, we have to make initial guesses which are reasonably close, close enough, close in the sense that we have to make sure that there is only one root between this x0 and x1. And then what we do is we find the midpoint of this, that we take x1 plus x0 by 2 as a new x2 value. Okay. So now we will find, so we took x1 here, x0 here, so which is x2 is equal to x0 plus x1 by 2. Okay. So now that will come somewhere here, and then we will find the function value at that point. Okay. So we have the function value at that point. Okay. Let me draw this a little far so that I can demonstrate it better. Okay. So the x2 would be somewhere here. So the x2 now, so f of x2 from this graph you can see that f of x2 is less than 0. Okay. So the two possibilities, you find x2, so you have first x0 and x1, then you found x2 which is a midpoint of x0 and x1, okay, and then we find f of x2. There are two possibilities, of course, we could be and three possibilities actually if you are lucky. So normally it is either 0 is greater than 0 or less than 0. The two possible. If it is less than 0, then what we do is we'll throw away x2 and throw away x0 and replace x0 by x2. Okay, now in this case we will say now x0 is now x2. Okay, so that is this x0 is being shifted to this point. Okay, and then we again find the mean of these two. Okay, now next time when we find the mean of that, it will be somewhere here. Okay, on this side of the thing. Okay, so that is the case. So next iteration we will have f of x2 greater than 0. So then we will replace x1 by x1 equal to x2. Okay. So in the next point, right? So we can see that if I take this as x0, okay, now I took the mean and that will be somewhere here. Okay, so then I will get it as positive, the function value. In that case, I will throw away x1 and then move my x1 here. Okay, so I have x1 here and x0 here, so I'm closing onto the 0. So that's a very simple idea of successive bisection. So let me summarize that here. Okay, so we have if f of x2 is greater than 0, then the root is, we know that between x0 and x2. So we'll replace x1 by x2, and if it is less than 0, then we'll replace x0 by x2. Okay. And now we and search in the interval between 1 and 2. So that's the basic idea. So then we have, so let's say take a function of this form, okay, complicated function. F of x is equal to 667.38 by x square into 1 minus exponential something minus x, exponential of minus 0.146843 x minus 15. So it's not easy to guess solutions of this, some nonlinear equation. So we'll take two trial points, okay, which enclose the root x0 and x1, right, and then we make that f of x0 and f of x1 are opposite signs. Right. So I'm just summarizing what we just discussed here, and so then we have the root like this. So that function behaves something like this, and we have the roots x1 and x0 here. Okay, so here x0 is positive, x1 is negative. Okay, so it's 2.5 and 5.5, and the root is somewhere here. From graph you can see, but if you have not plotted the graph, you don't know where it is. So you just taken two values of x0 and x1, okay, such that one is positive and other is negative. Right? And then we found the mean of that is equal to 4. So we shifted the mean of x0 and x0 and x1 is somewhere here. So that is 4, and the function value there is positive, right? That we can see. So we replace x0 by that. Okay. So we have our x0 shifted here. Okay. So you can see that in successive bisections, So we will continue doing this, okay, and then you can see that these two comes closer, x0 and x1 comes closer and closer, okay. And so that's the way we would finally arrive at the solutions. Okay, so we repeat this bisection procedure, okay, and we always enclose the roots in. So we always make sure that we enclose the roots in each interval, okay, and then as soon as we reach the accuracy which we need, or the precision we need, we will stop there. Okay, so in this case, the root of the function was 4.72. Okay, so that's what we just see. Okay, so now we will have to say, I just said that we have to look at the accuracy. We want to when we reach the desired accuracy, we stop it. Now the question is, what is the desired accuracy? Okay, so that also we will have to worry about. Okay, for example, in this particular case, we'll see that we will, by the bisection procedure, with each iteration, okay, with each iteration, we will half the interval, right? Because that's the scheme here. Each iteration here, the interval is halved. So we start from this, and then we go to that, okay, and then we go to this, etc. So we keep halving the interval. Okay, so in about 10 iterations, we would have gone about 1000. The interval would have shrunk to about roughly the order of 1000. Okay, so and now we have to be careful that we have to stop it somewhere when it hits the machine precision. Okay, otherwise it will get into an infinite loop. So we should not ask for accuracy which are beyond the machine precision. So that is something which you should be careful about. Okay. So now the question is, how do we actually come with an idea of what is the accuracy which we require and what is the accuracy which we can get? Okay, that's what we summarized here. That so we have to terminate this iterative scheme algorithm, okay, when we a predetermined criteria for the allowed error is met, right? So that's what we want to do. So we cannot ask the iteration to be continued till the f of x goes to 0 exactly, because it's a floating point operation. So we cannot get to exactly to 0. The function cannot go to 0, and also because when you do this scheme, okay, x0 plus x1 by 2, we will have some kind of round off errors coming. Okay, so beyond some iterations point, we will not be able to get any more accuracy. So we have to define a proper criteria. So we cannot, of course, define a criteria that depend on the knowledge of the true root, right? Because we don't know the true root. Okay, so we cannot define a criteria which based on the actual knowledge of the root, because we could actually have multiple routes to solutions, and we want to do actually an automated program. So we cannot define the criteria based on the knowledge of the. So these are algorithmic details. So since the function goes to 0 at the true root, okay, one such criteria is that the function value itself. Okay, so now here there is a problem. Okay, because the function value, we could say that in this kind of a program, this kind of a function, it might work well. So what's saying that, okay, now we know that the function goes to 0 at that point. So we could say that, okay, I could have, when the function value reaches the function f of x is close to some epsilon. Okay, so that is epsilon, some small number, okay, which is within the machine precision, okay, and then I can stop this iteration. So that's looks reasonable way of doing it. Okay, but again there is a problem here, because the way the function approaches the 0. Okay, so let's see that. Okay, that is, in this kind of a function it may be okay, but let's say the function is something of this form. Okay, that is. But that's again my 0 axis. Okay, so I'll just draw it there. So that's x axis, and that is my f of x. Now let's say the function is something which goes to 0 rather slowly. Okay, so it is like, okay, it's something like this, some function which goes like that. Okay, so in that case, now we know the root is here. Okay, but this slope could be very, very small. Okay, so in that case, if you put in that f of x equal to some small value is my root, that could be very far away from anywhere. It could be even here, but it could be even very far away. Okay. So because these values are so small, we could even have the whole range of x values for which we get the same, we get this answer that f of x is equal to epsilon. So when the case in this case is where we are actually looking at the 0 of the function, right? So the function going to 0 is not a good criterion, because if it goes with a small slope, okay, this can lead to an erroneous result. So that is one case where it would fail. So the best approach would be that to look at what is in each step, what do we get in each step. That is, you find the new x2 values, that is that we find a new x value, right, as our root, and we compare it with the old value and take the ratio of these two. Okay, so that's a better approach. Okay, so in this case, what we call the xr new is what we obtain from the bisection x0 plus x1 by 2. Okay. So we did this method here. Okay, so here, so we did that x0 plus x1 by 2, and we got it as here, right? So that's one value, and then we took this as x0, and then we did another iteration of x0 plus x1 by 2, and we got the value here. Okay, so that's x2 in the first step, and this is x2 in the second step, or this is called x2 old, and this is x2 new, let's call it. Okay, then I can do x2 new minus x2 old divided by x2 new, the mod of that. So that will be one criteria of an epsilon. Okay, so instead of looking at the function value itself, we look at each iteration how much it is jumping. So that will be okay in this kind of cases. Okay, so if this is not jumping too much, right? If the roots are not jumping too much, then we will be pretty close to the actual answer. So that's the idea. Okay, so that's a better method because this doesn't depend on the slope of the function. So the slope it doesn't depend on the slope of the function. So even in the cases where the slope is too small, this would work. Okay, so remember here what I call xr new is what we obtain from the bisection, that is x0 plus x1 by 2. And then what we call xr old is the one what we obtain from bisection the previous iteration step. Okay, so then we could have an epsilon a, which is now again on the machine precision. Okay, it's a predetermined value, but it normally should be higher than the machine precision, so that the round off errors does not take us into an infinite loop. Okay, attention should be paid to that fact. Okay, so now here is an example of such a routine. You can do it with a calculator. Okay, so we have a function of the form 1 minus x squared plus log 1 plus x equal to 0. Okay. So I make some guesses. Okay, so there's some guesses tabulated here, some guess values. Okay, so I say x0 is 0.5 and x1 is 2. So for x0, x equal to 0.5, this is a positive number. Okay, and for x equal to 2, this is a negative number. It's easy to see that, right? Okay, so then that means that my initial guesses x0 and x1 actually what do you call brackets the root. Okay, that's a technical term which you would use, that it brackets the root. It's on either side of the root. And then I take the mean of this, that x0 and x1, and I get 1.25. Okay. And then I look at the function value at that 1.25, it happens to be positive. Okay. So you remember now this is positive, x0 is on the positive side, x1 is on the negative side here. Okay. So f of x2 is positive. Oh, so what I would do is I would just replace this one, okay, by x2. Okay. Now I am bracketing my solution between 1.25 and 2. In the next step you can see. So in this case, to find the epsilon a, I have used x0 and x2 because this is what I am going to replace. Okay, so I take x0 and x2. Since this is what I am going to replace in the first step. The next step, it's obvious what we are going to replace, but here it's x0 and x2. So I take the difference between these two divided by 1.25 as my epsilon a. So then I replaced that by 1.25, okay, and then I took the mean of that. So I got 1.625, so x0 and x1. and that the function value at that point is negative. So obviously I am going to replace now x1 by this new value. So my new bracketing is between 1.25 and 1.625. So we continue this process. Again, we got the function value to be negative. Okay, so it's not necessary that we need to jump on either side, right? So we have, so in this case, again this function value is negative. So again we will replace x1 by the new value. Okay, by the new value, that's 1.4375. So now we have the bracketing between 1.25 and 1.435, and you can see that the error, the absolute error, that is the magnitude of this, is decreasing pretty fast. So in about 15 in this case in about 15 iterations, okay, we have gone to a very small error. Okay, and we find that our root is about 1.36389. Okay, so we have accuracy up to that. Right. So that is what we have obtained in this thing, and we can see that the error, the function has gone to, in this particular case, the function also has gone to very close to 0, and you can see that here that the function is already going to 0 very slowly here. Okay, and but the epsilon a, you can see how fast it is decreasing in this case. Okay, so definitely this is a better method of determining the accuracy of our root by looking at this epsilon a, which is x2 new minus x2 old divided by x2 new. Now that is an example of one such method. Okay. So now we could use similar method, and another one which is now, that was the simplest way, is to just to do bracketing and then do the mean, take the mean at every time step. We could slightly improve on that, and by using what's called a method of false position. So this method again uses bracketing techniques, that is, we need two guesses, x0 and x1, with f of x0 less than 0, f of x1 greater than 0. Either way, it does not matter. What this is a notation here we are going to use is f of x0 less than 0 and f of x1 greater than 0. But the difference is again that from this value of x0 and x1, we will go to the new values of a new value and replace one of x0 or x1 depending upon the new value we get is the x2, the f of x2 we get is positive or negative, the function is positive or negative at that. So it's same as the bisection method, it's not very different. So what's different is that the new value is not the mean of x0 and x1. Okay, we'll try to be a little more clever in this particular case. Okay. So now the new guess here is obtained by looking at where the line connecting the two that x0 f of x0 and x1 f of x1 meets the x-axis. So that's this here. I will just show that here again. So we had this case, okay, f of x0. So let's take this. Okay. So we had f of x0 and x1. So that was our initial cases. Okay, so we choose an f of x0 to be less than 0. So f of x0 is less than 0, f of x1 greater than 0. So now in the bisection method, what we did was to simply choose x1 plus x2 by 2. That's what our bisection method was. In this case, okay, in the method of false position, what we do is we take a straight line connecting this point to this point. Sorry, this point to this point. Okay, so we draw a straight line, okay, like this from this, okay, and then we say that where this line meets the x-axis, okay, that's the new solution. So that will be our x2 now. Okay, so that's the idea. So we write the equation of this straight line, okay, and find the intersection of that straight line with the x-axis. So that's what it is. Okay, so the new position. So we know how to write the equation of a straight line which connects 2 points x0 f of x0 and x1 f of x1, and it will definitely meet the x-axis somewhere. Okay, so then if this is crossing the x-axis because it changes sign. Okay, so you will get that intersecting somewhere on the x-axis. Okay. So then we will replace. We'll get a new x2 value, which is the intersection point of this. And the formula for that is this. Which we can easily derive from the fact that this that you can write the equation of the straight line x0 which connects x0 f of x0 and x1 f of x1 and take the 0 of that function, that straight line where it crosses a 0. Okay, so that gives us the new value x2. Okay. So then again we will replace x0 or x1 by x2 depending upon whether it is positive or negative. In this case x2 being f of x2 being negative. Okay. So in this particular case we will replace x0 by x2 and we have now thus two solutions. So now we have a point here and then the next straight line would be something like we have to draw a straight line between this point and this point. Okay, now that again cuts the axis here. So you can see it comes pretty close, very fast. Okay, this is definitely much faster. Okay, a little more complicated in the sense that we have a formula which is not as simple as x0 plus x1 plus x2 by x0 plus x1 by 2, but we have to find a solution of this, but it's still pretty simple, and then you can find a new root here in the next time, and then and you can see that that comes very close to the actual root. So that is okay. So as we remember that again that we assume here the function has opposite signs on either side of the root. That's important. Okay, that's a thing which you have to remember. Okay, so what's the method of false position? So we assume that we the function has opposite signs, and which is always true, right? And then we will make two guesses x0 and x1, such that they are on negative and positive, and then we will find the line connecting f of x0 f of x0 to x1 f of x1. Okay. And we will find the point at which that line crosses the x axis and let that point be x2. Okay. And then we have an expression for the x2, and then we will replace x0 or x1 by x2 depending upon whether f of x0 x2 is less than 0 or f of x2 is greater than 0. Okay, so again we will see this in the summary in a block diagram here. Okay, so here we'll again see that the false position method. So again we have taken the same function as that 2, okay, and then we again take the two functions that encloses the root, okay, and then the same as in the bisection. Take the same function and the same as in the bisection case, okay. And then now we will draw a straight line connecting these two functions, these two function points. Okay, that's what we have done, and that's our new point here, right? And then we will shift x1 to that new point. Okay, so we will have x1 shifting to this new value here. So that's what x1 is shifted to that point. Okay, and then we again have a new line now connecting this x0 and that function value. So now that is shifted to here. Okay, so that's the next step. Okay, so we keep doing this iteration again and again. Yeah, so we'll continue this iteration till we reach the desired accuracy. So that's what has been shown here actually. So that's in a sense this is very similar to what we saw in the case of the false position. Sorry, the bisection method, not very different. And we will again see an example of the use of this function using log of 1 minus x squared plus log of 1 plus x, as we saw in the earlier case. Okay, and we will see that this converges much faster than the one which we saw earlier, that is the bisection method. Okay. I will also see that the error here is decreasing monotonically. Okay. So, but there is a warning here that there are problems with bisection methods. Okay, so that is, you can see that yourself if you try to solve an equation of this form. Okay, so I encourage you to just look at this form for a function of very simple function x to the power of 12 minus 1 equal to 0. Okay, and you do this with the bisection method and also with the false position method, and compare your answers by plotting the error as a function of the iteration number and see how does it converge. Okay, so two methods you can try all these things, that either by taking x2 as the point at which this straight line connecting these two initial guesses crossing the x-axis, or by just taking the mean of this x0 and x1. So that's what we have seen so far. Okay. So both these methods need a good guess about where all the zeros are. Okay. So that's also another point. Okay. So we compare these two methods. One thing is that for bisection method this false position method would converge much faster. Okay. That's in some cases. But both the methods require some drawbacks, as common drawbacks, and that is one is that both requires all the zeros to be listed. Okay. So we need to know how many zeros are there, and we need to know where these zeros are, okay, before we proceed to find the answer. Okay. So one thing is how to list all the zeros. Okay. So one would be, of course, is to plot it and then look at it. Okay, so then the simplest scheme to list all zeros will be to start from one end and the interval, and whenever you look at all the points at which the function changes sign, or how many times the function changes sign. Again, here there is a problem that we have to go in a step size which is smaller than the distance between any two roots. Okay. So how do we list all the zeros? That's a question, right? So then in that question we will say that, okay, I start from one end and I keep going towards along this axis. And every time it changes sign, I know that I have passed one root. Okay, so I have 1 0 here, and then I pass here and I get another 0 because it changes sign, and etc. But again, this has a problem that the step size we use to go, right? We'll see that in an implementation of program, and when we look at a program, that wherever the step size we choose as we go along the x-axis has to be smaller than the interval between these roots. So if you go larger interval, that we might just miss. Okay, we might jump from here to here if you use a larger step size, and we say that we are not past a root. Okay, so we'll miss both the roots. Okay, that's possible. So we have to be small enough to increment. Okay, the increment used should be very small. So then the question is how small, and what is the value of that? So that's a problem with this. Okay, this methods. Okay, we need to have an idea about the sign. Okay, so its advantages to have to use methods which doesn't use this kind of bracketing methods. Okay, that's something which we should be looking at now. Okay. So again, there's one more problem here. So we'll try to bracket all the zeros of this function, not the solution, just bracket all the zeros of the solution by some method which we're using different step sizes. Okay. Sine 10x plus cos 13x. So you could just try to bracket all the zeros of this function. Don't try to solve for it, but just bracket it, and then you plot this function and see whether you have obtained all the zeros. Okay, just to demonstrate that you do have a problem with the step size determination, or just to get a feel for this step size determination problem. So we see that the common problem with both bisection and the method of false position is this determination of the zeros. That's the biggest hurdle. Otherwise, it's an extremely simple method. Both are extremely simple method to implement. Okay, so we just have to make one guess, and then we can continue doing that. We're finding a 0, and once you found 1 0, right, once you found, we've started with 1 x1 and x2, and we found one function, 1 0 point, and then we could just take the initial guess as a little above that. Okay, and then we again bracket these solutions. So once we have found 1 0, so let's say in this case we found solution 1. Okay, so let's say one solution we found here is xs. Okay, that's our solution xs. Okay, so and then the next solution, to find the next solution, we could start with an initial guess at which one value slightly higher than this. Okay, and then another value where the function has changed sign. Okay, so you again go look for where the function changed sign, and then start with another value there. Okay, and then you can again bracket that, and then it will converge to that root. So once you found one root, it's easy to go to the other root. Okay. But again, when you search for the zeros, when we search for the points at which function changes sign, okay, you have to be careful. So that's the most important point here in both these methods. And there's two important points to take care when you write a program on this. One is that you have to make sure that you have enclosed all the roots, and the second thing is that the accuracy you demand, that is x old minus x new divided by x new, the modulus of that should not be more than the machine precision, such that we will not get into an infinite loop because of the round off errors. So that's something which you have to be careful. Okay, so now we look at some methods, okay, which doesn't use the pre-knowledge of the zeros of the function, okay, and they're called direct methods. So this we saw this in the methods in which we need some idea about the solutions. So now we will look at some methods which will not use that. Okay, so what are the previous things which what we just saw? So that is, we saw that it's an iterative scheme, and we saw that it needs two guess solutions on either side of the zero of the function. Okay, so we need a pre-knowledge of the zeros. Okay, so that's a basic sum. Okay, so now we will look at cases we need two guesses on either side of the zero is not needed. So because we might have the function value itself is given by some other program in which we will not be able to scan the whole thing and find out where the zeros are. Okay, so in that case we need a slightly different method. So basically what we are saying is that we need to make we need a method in which the best at the worst, okay, we need to make only one guess. It will be very nice if you had a method in which we don't need to make any guess at all. Okay, so we want to find a solution of a nonlinear function, okay, in which we don't want to make any guesses. Okay, that will be the best. Okay, or at worst we want methods in which we make only one guess. Okay, so that is so that we don't have to have an idea about where the zeros are. Okay, so that is one guess that it can be on either side of the zero, right? We don't want it to be that always to one side of the zero. So it can be anywhere on the side of the zero. Okay, so we will look at some methods which uses this form. So that is one is the fixed point iteration method. So in the fixed point iteration method, we will convert the function f of x. So that's the next method which we are going to look at. Okay, so it's called the fixed point iteration method. So here what we need is again one guess. We need to make one guess. Okay, so we have a function of the form f of x equal to 0. Okay, so that's what we have. Okay, so as before, so some function f of x equal to 0. Now what we want to do is we will make one guess. Okay, so that is x equal to x1. Okay, as x equal to x1, that's the solution. We say x1 is our guess, the first guess. Okay, x equal to x1, and then from that we want to go into the 0, that is the value at which this goes to 0. So in the case of the fixed point iteration, we need to write the function f of x as g of x minus x. Okay, so that's the must. You should be able to write this function f of x as g of x minus x, and then we can say that where f of x goes to 0 is same as saying that x is equal to g of x. Okay, so this equal to 0 implies, right? So that implies x equal to g of x. So that's the basic idea behind the fixed point iteration. Okay, so we start with one guess, and we have this g of x equal to x. Okay, it's like kind of a map. Okay, and then we say that the next iteration point is obtained by. So we just start with one guess xi, and the next point xi plus 1 is given by g of xi. And you can see that if this is actually a solution, your guess xi is a solution, then this is an identity, right? So you get new xi plus 1, it will be same as xi. So that's the idea. So the error would be xi plus 1 minus g of xi divided by xi plus 1. So now I just show you this method graphically again here. So and then we will come back to here and then discuss where this method can fail and where this method can actually work better. Okay, we will look at that now. Okay, so here is the fixed point iteration. So we write f of x equal to 0 as x equal to g of x. Okay, and then so we will start with some guess. Okay, so we have converted that as x equal to g of x, right? So we can start from some guess, and then we will write xi plus 1 as g of xi. Okay. So then we will continue this. Okay, so that's basically the graphical representation of this. Okay, so we have a function like this. And it's basically what we are trying to find is this y equal to x line, this intersection point. Okay, that's our idea. Right? Okay, so we start with x equal to 0 here, and then we want to converge onto that root. Okay. So we started with some function. This is a graph here which shows x and g of x, right? And we started with some guess. Okay, some guess x0, right? And then we generated the function g of x. Okay, some guess x0, and we got a new x value from that. Okay, and the new x value, and then we went to the next g of x, and then that gives us a new x value here. Okay, that gives us a g of x here. Okay, and then that gives us a new x value here. Okay. So this is the line y equal to x. Okay, so by writing x equal to g of x, basically what we are trying to find is graphically this means this. Okay, so that is, so g of x function is like that, and then y equal to x function is this, and we want something which satisfies both, right? That means we want the intersection point of that, right? We have y equal to x and y equal to g of x, right? It satisfies our x value should satisfy both. So that means that we need where this y equal to x line intersects the g of x. We want to find that iteratively. Okay? Graphically it's easy, we can always read that off here, but iteratively we want to find out. And that's what been shown here. So we started with an x0 value, right? So that's the g of x corresponding to that is given by this height, right? So that is our next x value. Okay. So that x value is this, that is corresponding to g of x. So from that x value we found out the g of x, that is here. Okay. So that's our next x value, that is x2. Okay, and then we found the g of x from there, and then we'll finally converge it onto this point, rather slowly, but we'll surely converge it onto this point here. Okay, so again we'll see that this will work only when the slope of the g of x line is less than 1. Okay, otherwise it will diverge. Okay. So we'll make progress here, but it's rather slow. And one more important point to remember is that it will not converge when the slope of the g of x line is greater than 1. Okay, that's what I'm trying to show here. Okay, so now here is a function, and you want to find the 0 of this function. So if your initial guess was here, we could find it will converge here. Okay, now this function, the g of x function, has a slope which is less than 1. Actually, this is negative slope here. Okay, and you started from here, and then this will converge pretty fast onto this. But let's say we started somewhere else. Okay, so our initial guess was, again, it's only one initial guess we have to make, only for x0, but we made it somewhere here. Okay, and hoping that we will converge onto this point, but we will not. Okay, because the slope of this function here is larger than 1. Okay, so what we basically find is that it doesn't intersect. So this just goes away. So that's a problem with this method. Okay, so we should be able to write the f of x equal to 0 as x equal to g of x function, and we also need the initial guesses at points where g prime of x, that is the derivative of g, is less than 1. Okay, the g prime of x should be less than 1. Okay, the two values has to be satisfied. So that's something which you can easily see, right? So by just taking the g of xi plus 1 minus g of xi, okay, divided by xi plus 1 minus xi, that will be the slope of this, right? And comparing that with our xi plus 1, xi minus, so we are writing this equation here as xi plus 1 is equal to g of xi, right? And so we can easily see that g of xi plus 1 minus g of xi divided by xi plus 1 minus xi. Okay, if you write something like this, so g of xi plus 1 is in our case would be xi plus 2. So the g of xi is xi plus 1. That's what we get. Okay, and we have xi plus 1 minus xi. And we want this to be, this is the distance between the two guesses, two roots. The distance between the two guesses or iterative, the results in the iteration in the I plus 1 step, and this is the distance between the roots at the ith step, and we want this to be less than 1. Okay, and this is the g prime. Okay, so we know the g prime has to be less than 1 for this to work, otherwise this will diverge. Right. So we need the g prime, that is the derivative of g prime, to be less than 1 for this iterative scheme to work. So that will be the drawback of this particular scheme. So even though only one guess has to be made, this still have a drawback here, that is that we need g prime of x to be less than 1. Okay, so that's an important problem with this method. Okay. Again, you could find the solution of as a problem. You could look at a function of the form x minus cos x equal to 0. It's an easy problem, but it obviously can be written as x minus g of x. Now g of x can be easily identified as cos x here, and you could just find the root of this. Okay, start with x equal to 0.5, and you can see how fast it would converge. So we'll find the g of x value, and then that is so I just also written the f of x value here. Just this has to go to 0. That f of x now is x minus cos x, right? Okay. So I just look at the g of x. Now the g of x is the new x value, right? And then I again find the g of x here, and then replace x by that, and then you go by this iteration scheme. So finally you have to reach x is equal to g of x. So we'll find that in this particular case we have gone to something like 15 iterations, and it's okay. The error is still not very low, but the function has gone to close to 0. So that's again the problem of the slope. Okay, so there's one more problem, which would be to find the root of the equation x minus e to the power of x plus 2 equal to 0. Okay, so you could do this problem with all the three methods which we have now so far looked at. That is the bisection method, the method of false position, and this fixed point iteration. Okay, so we have three methods we looked at: bisection, the method of false position, and the fixed point iteration. So you could do this problem, that is x minus e of x plus 2 equal to 0 with all the three methods. Okay, you could, in the case of fixed point iteration, we need only one guess, so we could do it from x equal to 0.5 and x equal to 1.5 as the two different guesses. Okay, so that's a summary of the method which so far we have looked at. Okay, so now we could in the next class probably we would look at some other iterative scheme, again another iterative scheme. Okay, but again which uses only one particular only one guess. Okay, so the problems in which we need, or the methods in which we need two guesses, are only fixed point iteration and the method of false position and the bisection. Okay, that's the two methods in which we need two guesses, and we need the two guesses such that it brackets the zeros. And if you have many zeros or many roots, then we need many such guesses which will bracket all the roots. In the case of fixed point iteration, we need only one guess. Okay, and that is could be anywhere, but it should be such that the function, the derivative of g of x, that is, we write f of x as x minus g of x, and we need the derivative of g of x at that around that point to be less than 1. Okay, such the thing. Okay, now we look at another method that is called the Newton-Raphson, again an iterative scheme. Okay, which is similar to the method of the fixed point iteration. So that's what we would be discussing in the next class. We will also look at some of the implementations of the ideas or the methods which we discussed in this class in the next one.